h equal to infinity.
Okay.
But we will go to h equal to normal finite number and then go to infinity. Yes?
Are the 5 components usually equal to double?
Yeah. So what happened? Okay? Okay. And then this, by the way, is a MDP for finite state space and finite action space. You can generalize this to infinite state space, continuous state space, and continuous action space. We won't talk about it here, but generally wherever in this class we will see a big summation, sigma. In your mind, if you convert it to an integration, then that's continuous. Okay, but we won't normally talk about it here. Okay, the last thing, one more thing about the variation on MDPs is reward versus cost-oriented MDPs. Until now, I looked at, so you can look at life in two different ways, and both are equally good. I mean, as I said, a glass is half full, a glass is half empty. They're objectively true. You know, it's just in one case you're thinking about what's missing, in another case you're thinking about what's there. Right? Similarly, you can think of life is a happy place and it ends with huge happiness. That will be the reward view. Life is a huge drag and then you die. That's the cost view. Both are true. Right? Both are completely true. Okay? So you could model MDPs this way in terms of RSAS dash. For each transition, you get a reward. What a good boy. Give some money. And so if you are getting bad, it's not actually a good boy reward. If I'm yelling at you, then I say I'm getting negative reward. Negative reward is positive cost. Right? And then the opposite is alternate model is cost-based MDPs, where you essentially say each transition incurs an immediate cost. Each transition incurs an immediate cost. And that would again, in most general cases, be CSAS dash. And then the goal here is to come up with a policy pi that maximizes the expected cumulative reward that the agent gets from every state. And the name of that is the value. The expected cumulative reward is called value. And maximizing it, that's the optimal value V star. You tend to think in terms of V star. In the case of cost view, in fact, that net benefit A star will be thinking in terms of cost view. Right? And the cost view, the goal is to come up with a policy pi that minimizes the expected cumulative cost from every state. Again, you want expected because there is stochasticity. You run the same policy twice, it gives you different sequence of states. Okay? This one is called J star. This is the view, rosy view taken in the reinforcement learning community. People tend to think in terms of rewards because the reinforcement learning as a word came from psychology. And Skinner, the behaviorist, started talking about this, and they were basically trying to train rats to do well in mazes. And he thought, what are people but slightly bigger rats? And so that's reinforcement learning. In fact, there are interesting stories that Skinner would have a Skinner box for Skinner's kid. And then Skinner kid must have probably sued him afterwards. But that's a different story. Okay. This is the RL view. This, on the other hand, is the view taken in the search and control theory literature. How many of you have heard of control theory? Anybody with electrical engineering background would have heard of control theory. It turns out that many different areas are trying to solve the same problem. Operations research is trying to figure out what's the best decision to take. Control theory is trying to figure out what's the best decision to take. AI agent is trying to figure out what's the best decision to take. Of course, for all the agents, AI is the most beautiful because it's in blue with pink. And also it's the most popular subject right now. And so those people are saying, we have done all this stuff, guys. In fact, we have done this before you guys. In fact, How many of you recognize this guy? He's a new young faculty member joining our department. And his name is Dmitry Bertsekas. He was, for all his life, he was an MIT decision sciences professor, and he has done tons and tons and tons of work in control theory and what basically MDPs from a control theory perspective. And my joke is that Dmitry writes books the way other people write papers. He has like 15 or 20 books. And he's a pretty amazing guy, and he's coming here. The interesting thing is, so when he came, because he's coming here, ASU Engineering is obviously celebrating this. He'll be a CTC faculty member. It's celebrating it, so they wrote an article, and they took a mugshot of him, with him vandalizing our brickyard wall. What is he vandalizing it with? J-Star. J-Star. There is only one principle in life, which is computing the optimal cost to go. The man made his entire career and 18 or so books based on this. Okay? And in fact, it just says the optimal cost to go of a state S, state X, is minimum of over all U's, the cost of going from X to U using G. There is no G. Dmitry actually likes to think in terms of cost. So in cost-oriented people think in terms of cost up to that point, the G value. So G of XU plus the neighbor's J star value. And this, by the way, is called Bellman's optimality principle. And if you are into religion and computer science right now, you should pray for it. Because this is one of the most important equations that you will see, and it will actually cover your life for the next several classes plus the rest of your life. And so in this particular case, notice what they're doing. They're minimizing. So in fact, what we are saying is we don't know how to compute the optimal cost to go, but it will have the following property. My optimal cost to go would be connected to my neighbor's optimal cost to go. So if I'm here, I can go to this state, this state, this state, this state. If I happen to know their optimal cost to go, and I know the cost of and probability of me going to those states, then I can compute my optimal cost to go. That will come from the node that is the best neighbor. In particular, the best action that I can take from wherever I am. And this winds up basically what we are doing here is this minimization. You will see the same equation next class. With instead of J, you will say V star, and instead of min, you will say max. Because for rewards, you want to maximize instead of minimize. Stop here. You can come.